Okay, let's unpack this. Imagine you're faced with learning something uh, completely foreign.
Right.
Maybe it's a complicated new board game, layers of rules, hidden information, or maybe diving into a new programming language with a totally different way of thinking about
Yeah,
problems.
that initial struggle is familiar.
How do you even approach that? You don't usually just like read a manual once and bam,
Yeah,
like you're an expert, right?
definitely not. It takes, well, interaction.
Experimentation.
Exactly. You try something, you see what happens, you learn from the feedback. Maybe a game piece moves wrong or your code just throws an error.
Mm-hmm. The
Yeah.
feedback loop is crucial.
You adjust your strategy, and it's through that trial and error, really, that you gradually build up understanding and, skill.
Right.
Now, think about that whole process, that active iterative learning through interaction. But instead of a person doing the learning, it's an AI.
And the ambitious goal isn't just mastering one specific thing, like one game or one language. It's about learning how to learn, how to strategize, how to explore, and how to adapt across this huge universe of different interactive challenges it might run into.
And that capacity, that general strategic exploration and learning from interaction, that's precisely the kind of ability we need to give AI agents if we want them to operate effectively in complex, unpredictable environments.
Yeah.
It's really a foundational step towards making them more autonomous and capable systems.
And that's exactly where we're heading in this deep dive. We're focusing on a really fascinating piece of research that tackles this exact problem, teaching large language models, these powerful text generators everyone's talking about, to become more than just responders, but proactive, generally curious agents, agents capable of strategic decision-making and effective exploration in all sorts of different interactive settings.
And the source material for this is a pretty comprehensive research paper. It introduces a novel fine-tuning approach, specifically designed to kind of cultivate these capabilities. It's called PAPRIKA.
PAPRIKA. I like the name. It makes me think of something, I don't know, vibrant, maybe a bit surreal, like exploring different worlds. Is there a story behind it?
Yeah, there is, actually. The paper mentions in a footnote it's inspired by the 2006 anime film PAPRIKA.
Oh, really?
Yeah, in the movie, there's this detective who uses a special device to navigate through people's dreams, these diverse, often pretty strange dream worlds, to solve mysteries.
Okay.
And the researchers felt it was, a fitting metaphor for an AI agent that needs to be able to explore and operate within a really wide variety of distinct interactive environments to achieve its goals.
That's brilliant. It really does capture that spirit, doesn't it? Navigating different complex, maybe unfamiliar interactive spaces. Okay, so our mission for this deep dive then is to really get to grips with this PAPRIKA framework. We want to unpack what it is, understand in detail why teaching this kind of general strategic interaction is such a critical challenge for AI right now, then dig deep into how PAPRIKA actually works under the hood, its core components, the data it uses, the training process, and maybe most importantly, what the results of this research tell us about the potential for building AIs that can genuinely interact with and learn from the world around them.
What problems does it really solve that previous methods couldn't? And what does it promise for the future of AI agents?
Exactly. Where does it move the needle?
Let's dive in and unpack it.
So, as we've talked about a lot on these deep dives, large language models, LLMs, they're incredibly powerful tools, right? Processing, generating text, answering questions, summarizing things, writing creatively, having conversations.
Yeah, they've gotten surprisingly good at predicting the next word, essentially.
But making them truly effective autonomous agent systems that can pursue complex goals with, minimal human help by acting in and interacting with external environments to get stuff done that feels like a whole different ballgame.
It is. It's a significant leap.
Why is this kind of strategic interaction so fundamentally difficult for LLMs, even with all their amazing language skills?
Well, it really boils down to a few key issues, mostly related to their training data and just the nature of interaction itself.
Okay.
Firstly, the vast majority of the data these LLMs are trained on, huge amounts of text and code from the internet, books, whatever, it's fundamentally static.
Like a snapshot.
Exactly. It's a snapshot of information, language, events. But it doesn't inherently capture the dynamic structure, the context you need for sequential decision-making and interaction.
So you might see a transcript of a conversation, maybe?
Right, you see transcripts, sure, but not the full turn-by-turn process of an agent actually trying something, seeing what the environment does in response, and then adapting its next move based on that specific feedback loop. And that loop can go on for many, many steps.
Yeah, it's like reading a summary of a chess match versus actually playing it, feeling out the opponent's moves, making mistakes.
That's a great analogy. There's just a lack of explicit, rich data showing how actions lead to consequences in different kinds of environments over time.
Okay, lack of the right kind of data. What else?
Secondly, and this is a huge practical hurdle and a safety one, directly training autonomous agents by just letting them interact and learn in the real world. It's incredibly risky, it's expensive, and often it's just not feasible at the scale you need for training these massive models.
Right. I mean, you can't just let an early stage AI loose in, say, a power plant control system or even a complex financial market to learn by trial and error.
Exactly. Or even just interacting with real people in sensitive situations. An agent making unguided critical errors could have, well, severe negative consequences. It's just not a scalable or safe training method.
Makes perfect sense. Too dangerous, too costly.
Precisely. And thirdly, even the traditional methods used in reinforcement learning, or RL, which is designed for training agents in interactive environments, even those can struggle when you combine them with the unique nature of LLMs and this need for general capability.
How so?
Well, the paper points to prior work showing that standard LLMs, even if you try to prompt them cleverly, often perform quite poorly on tasks that seem simple but require strategic planning over time, like multi-armed bandits.
Ah, the slot machine problem, figuring out which machine pays out best by trying them.
Yeah, basically. You have to strategically explore different options, balance learning about them with exploiting the one that seems best so far. LLMs weren't naturally equipped for that kind of strategic information gathering and adaptive decision-making over multiple turns.
They're good at language, but not inherently strategic planners in that interactive sense.
Right, and for many complex unfolding interactions, there isn't always a simple set of instructions or a known algorithm you could just, copy-paste into the prompt to make it work.
Okay, so let me see if I've got this. The
Hey.
big problems are, 1, the usual training data is static, doesn't show interaction well. 2, real-world training is too risky and expensive. And 3, LLMs aren't naturally strategic explorers or decision makers in these interactive settings, and simple prompting often isn't enough.
That captures it perfectly. The fundamental challenge is teaching them not just to understand and talk about interactions, but to actually perform the strategic sequence of actions, observe the results, and then adapt their internal state in what they do next, based on that feedback from the environment.
And doing it efficiently, safely, and in a way that scales across tons of different interaction types.
Exactly.
Which definitely suggests we need a different approach,
Yeah.
not just bigger models or more static text.
Absolutely. And that's where the paper proposes this paradigm shift. Instead of trying the impossible training an LLM on every single specific interaction task it might ever encounter.
Which is infinite, basically.
Right. It's infinite. Instead, the focus should be on teaching the model the general process of solving problems through interaction.
Ah, okay. So teaching it how to learn in an interactive setting.
Precisely. The goal is to train it to interpret the feedback it gets from the environment in context, right there in the middle of the interaction, and adapt its behavior accordingly. It's similar to how in-context learning lets LLMs adapt to new text tasks with just a few examples.
Like giving it a prompt with a couple of question-answer pairs, and then it can answer new questions in that style.
Exactly. But applying that same idea, learning from the immediate context, to the domain of reinforcement learning and sequential decision-making.
So it's like teaching it the meta skill of in-context reinforcement learning, giving it the ability to use the current situation, the history of the interaction, the feedback it's getting, even if it's a totally new task.
To guide its decisions effectively without needing specific training on that exact task beforehand.
Okay, shifting from training on specific problems to training the general skill of interactive problem solving.
That's the core idea, yes.
And this is where PAPRIKA enters the picture as their proposed solution to achieve this.
Indeed. PAPRIKA is presented as a scalable method specifically designed to instill these crucial capabilities: strategic exploration, sequential decision-making, adaptation into large language models.
So the big picture idea is they use synthetic data generated in simulations.
Yes, synthetically generated interaction data. But the critical part, the real key, is that this data comes from a diverse set of tasks.
Okay, diverse simulated interaction data.
Precisely. The central concept is fine-tuning an existing LLM on a specially built dataset, This dataset is made up of trajectories, the step-by-step records of interactions generated within a wide variety of simulated decision-making tasks.
And the thinking is, if you show it enough different kinds of challenges.
The hypothesis is that by exposing the model to many different types of interactive challenges, all requiring different kinds of strategic thinking, information gathering, adaptation, it will learn the general decision-making skills.
And those general skills will then, what, transfer?
Exactly. Transfer effectively to entirely new, unseen interactive tasks without needing any specific prior training on those new tasks. That's the big goal. Achieving zero-shot transfer of decision-making capabilities.
Okay, I think I get it. So it's not about making the AI the world champion at, say, the game Mastermind by just drilling it on Mastermind over and over.
No, not primarily.
It's about training it on Mastermind in 20 questions and maybe some text-based adventure games and some simulated customer service interactions.
Right, a whole portfolio of different challenges.
So that it pulls out the underlying principles like deduction, strategic questioning, how to explore efficiently, planning ahead, principles that apply across all of them. And then when you throw a completely new puzzle game at it, one it's never seen, it can actually tap into those general skills it learned from the diverse training and figure out how to play, how to succeed.
You've absolutely nailed it. Teaching the general process, the underlying strategic thinking, rather than just expertise in one specific task.
Okay, that makes a lot of conceptual sense. But the devil's always in the details,
No,
right?
it's not.
How do they actually do this? Let's break down the PAPRIKA framework. What are the core components? Where do they even start?
Okay, the first step, and you could argue it's the most critical one, is the design of that diverse set of tasks.
Right, the training ground.
Exactly. The paper is very clear. The foundation of this whole approach is creating a suite of interactive tasks that, taken together, require a broad spectrum of skills. Strategic information gathering, sequential decision-making, adapting to feedback, if your training tasks are too similar, too narrow.
The skills it learns won't be general enough. It'll overfit to just that type of task.
Precisely. Diversity here is absolutely key for learning general principles that transfer.
So how diverse did they actually make it? How many different kinds of challenges did they build?
They designed and implemented 10 distinct task groups for this research. And these weren't just, slight variations of the same game. They were carefully chosen to exercise a really wide range of different abilities.
10 different groups. Okay, this is where the rubber meets the road. Can you walk us through some examples? What kind of skills does each one really demand from the AI?
Absolutely. Let's dig into the specifics. Drawing from the details in the paper's appendices, this is where you really see the richness of their approach.
Yes, please, lay it on us. What kind of games did they have these AI agents play?
Okay, so they included several classic deduction and information gathering games. First up, 20 questions.
A familiar one. Ask yes/no questions to guess something.
Right. The agent has to guess a hidden topic, could be a person, place, concept, whatever, within a limit, usually 20 yes/no questions. The crucial skill here is really strategic questioning. You want to ask questions that maximize the information you gain with each turn, things that really cut the possibilities down quickly.
Like asking, is it alive, rather than, is it Abraham Lincoln, right at the start.
Exactly. And the paper notes, they made this harder than some previous attempts by using a much larger and more diverse set of potential topics. They generated nearly 1,500 training topics and over 350 test topics using specific prompting techniques on GPT-4 Mini.
Wow, okay, so a big pool of things to guess. How did the AI actually play this? Who answered the questions?
They used GPT-4 Mini as the environment, the entity that knew the secret topic and provided the yes/no answers. But interestingly, they also used another LLM, also GPT-4 Mini, as a separate judge.
A judge? Why?
To verify if the agent's final guess was actually correct. And importantly, to filter out cases where the environment LLM might make a mistake, maybe give a wrong answer, or signal success too early. They call this environment hacking. The judge ensures the interaction followed the rules correctly.
Huh. Using one LLM to simulate the game and another to referee it, that's quite a setup just for one task. Shows the complexity.
It really does highlight the challenges of using dynamic LLMs as environments. They also included Guess My City.
Okay, similar idea.
A variation, yeah.
Yeah.
Still guessing a hidden location, but it allows for broader question types, not just yes/no. You could ask about, say, famous landmarks, local food, maybe historical events associated with the city.
So more flexible questioning, but still deduction.
Right. The core skill is similar deduction, strategic info gathering, but the format is more open. And again, they use GPT-4o Mini for both the environment answering questions about the city, and the judge, making sure the city name wasn't revealed directly, only confirming a correct guess.
Got it. So those two tasks really hit strategic questioning and deduction, especially in these more knowledge-based, flexible environments simulated by LLMs. What about tasks with really strict logical rules?
Yeah, for those, they actually found that using hard-coded programs, not LLMs, was more reliable for the environment. A prime example is Wordle.
Ah, the word puzzle everyone got obsessed with.
Exactly that one. The agent has to guess a secret 5-letter word, limited tries. After each guess, the environment gives very specific feedback. Green for correct letter in the right spot, yellow for correct letter in the wrong spot, gray for letter not in the word at all.
Pure deduction based on that structured feedback.
Pure deduction. And the paper specifically mentions using a hard-coded program for the Wordle environment because apparently LLMs sometimes struggle to consistently follow those exact feedback rules.
Interesting. LLMs aren't always perfectly logical rule followers then.
Not always, especially with complex rule sets. And here's a key finding for Wordle. They discovered a significant performance boost by using chain of thought, or COT, prompting for the agent.
COT prompting. That's where you have the AI think step by step before giving its answer.
Exactly. So before making its next guess, the agent internally generates this reasoning process. Like, okay, the feedback was A is yellow, P is green, L is gray. So possible words starting with P that have A somewhere else could be that kind of internal monologue.
And that helped it play Wordle better.
Substantially better.
Ah,
It forces a more structured, logical approach, which is crucial for a game like Wordle. They also included Mastermind.
another classic code-breaking game.
Right. Similar logic puzzle. Guessing a sequence, in their case, a 4-digit code and getting structured feedback. Number of correct digits in the right position, like Wordle's green. And number of correct digits but in the wrong position, like Wordle's yellow.
And again, hard-coded environment, COT prompting.
Yes, same setup. Hard-coded environment for reliable feedback, and COT prompting for the agent to structure its deductions. The paper notes they actually generated more data for Mastermind 100 trajectories per task instance instead of the usual 20, because the base models apparently struggled more with this one initially. Need more examples.
Okay, so those cover deduction, handling structured feedback, and the importance of internal reasoning steps via COT. What about tasks that feel less like traditional games? Maybe more like interacting with a system or a simulation?
They designed tasks for that too. One really unique one is cellular automata.
Cellular automata, like Conway's Game of Life,
Yeah.
that kind of thing.
Sort of related conceptually. Here, the agent's goal is to figure out the simple binary transition rule that governs how a string of zeros and ones changes from one step to the next. It sees input-output, pairs the string before and after the rule is applied.
And it has to deduce the rule itself.
Exactly. The agent guesses a rule, represented as a string. The environment, which is hard-coded, then takes that guessed rule, applies it to a test input string, and shows the agent the result. It's like getting feedback from an interpreter.
Ah, so the agent proposes a program, the rule, and the environment runs it and shows the output.
Precisely. And the agent then uses this feedback to refine its guess for the rule, iteratively. This specifically trains the model's ability to interpret feedback from a deterministic system and refine its code or theory based on that loop.
That's fascinating. It's like teaching it a mini debugging cycle based on system output. Very cool.
It is. Then there's Battleship.
The naval warfare grid game.
Yeah, a great example of balancing exploration and exploitation. The agent targets cells on a grid, trying to find and sink hitting ships. The environment, again hard-coded, gives simple hit-or-miss feedback.
So you explore the grid to find ships, then exploit the hits to sink them.
Right. The agent needs to strategically explore unknown areas, but also, once it gets a hit, switch to exploitation mode, targeting adjacent cells to sink the ship efficiently. It requires spatial reasoning and adapting your strategy based on the evolving state of the board. This also used COT.
Okay, so spatial strategy, explore, exploit, balance covered. What about tasks involving more like natural language interaction, but still with a specific goal?
That's where tasks like customer service and murder mystery come in. For these, they went back to using another LLM GPT-4 Mini again to simulate a dynamic, open-ended textual environment.
Okay, how did customer service work?
In customer service, the environment LLM plays the role of a non-technical customer who has a hidden technical problem, like maybe their internet is down or an appliance is broken, but they can't describe it well.
Okay.
The agent LLM acts as the customer service representative. Its goal is to ask clarifying diagnostic questions, to figure out what the actual underlying problem is and then propose the correct solution from a predefined list.
And I assume the judge LLM comes back here.
Yes, exactly. An LLM judge verifies if the solution the agent proposes actually matches the customer's hidden problem and, again, filters out any environment hacking, like the customer LLM accidentally giving away the answer.
Got it. So it simulates a real-world scenario needing information gathering through dialogue to solve a specific problem.
Precisely. And murder mystery takes that kind of dynamic text interaction even further.
Ooh, like a text adventure game?
Pretty much. An
Yeah.
LLM simulates a whole complex scenario, maybe a mansion, several characters with different motives, clues hidden in different rooms or conversations, maybe some red herrings.
And the agent is the detective.
The agent LLM is the detective. It has to navigate this environment by choosing actions like ask character X about Y, examine the library, check alibi of character Z. It gathers information piece by piece, interprets textual descriptions of clues or answers, and has to make deductions over many turns to identify the culprit.
Wow, that sounds way more complex and open-ended than the logic puzzles.
It definitely requires sustained strategic information gathering and some pretty complex reasoning over potentially ambiguous text interactions. And yes, an LLM judge is crucial here too, verifying the final accusation and making sure the environment doesn't accidentally give the game away.
Those two sound like they need a different kind of strategic thinking, less pure logic, more about navigating ambiguity, managing dialogue, integrating clues from different sources.
They absolutely do. It's about asking the right questions, interpreting potentially vague or even misleading information, and piecing it all together. Okay, almost there. The last task group they included was the classic bandit best arm selection task we mentioned earlier.
Right, the multi-armed bandit. Explore versus exploit.
Exactly, a pure reinforcement learning challenge. The agent sees several arms or buttons. Each one, when pulled, gives a reward based on some hidden probability distribution. The agent doesn't know these probabilities initially.
So it has to try them out.
Over a limited number of turns 20 in their setup, the agent has to decide. Do I explore by trying out arms I don't know much about yet, or do I exploit by repeatedly pulling the arm that seems to be the best one based on what I've seen so far?
And the goal?
The goal is to identify the single arm with the highest average reward by the end of those 20 turns. This is a multi-turn version, requires balancing that explore-exploit trade-off over time, use COT, and the rewards for each arm are randomized every time the task ran.
Okay, wow, that's a seriously diverse set of 10 task groups. You've got strategic questioning, 20 questions, guess my city, pure deduction, Wordle mastermind, iterative refinement from system feedback, cellular automata, spatial explore-exploit, battleship, complex dialogue-based info gathering, customer service, murder mystery, and classic RL explore-exploit, bandit. That really covers a lot of ground.
It's designed to. That diversity is the bedrock. So that's
Okay.
component one, designing the tasks.
What's the next piece of the PAPRIKA puzzle then? You have the environments, now you need the data.
Exactly. Component two is generating the diverse data set from these tasks. So they take the initial LLM model, the one they want to improve, and have it interact with these task environments they've built. This generates a data set of interaction trajectories.
Trajectories meaning a whole sequence, like turn 1, ask X, observe Y, turn 2, do Z, observe W, all the way to the end.
Precisely. The full record of actions, observations, and any internal reasoning, like chain of thought steps. But again, the key isn't just generating data, it's generating diverse data.
Right, you mentioned diversity being crucial. Why, again, remind me.
Because the goal is teaching general strategies. If all the training data just showed one specific way to solve, say, Wordle, or one narrow questioning strategy for 20 questions,
The model would just learn that one trick.
probably, it would likely overfit to that specific approach and then struggle badly when that trick doesn't work, or when the task is slightly different. Seeing diverse trajectories, different ways to approach the problem, different lines of questioning, even examples of failed attempts and how to potentially recover, that exposes the model to a much wider range of possibilities.
It learns a broader toolkit of strategies.
That's the hope. It learns what works, what doesn't, and maybe even why, across different situations within a task type.
So how do they actually ensure this diversity when they're generating the data? Do they just run the agent lots of times?
They run it many times, yes. They sample a large number of trajectories for each specific instance of a task, usually 20 trajectories per instance, though they did up to 100 for Mastermind because the base model struggled more there.
Okay, lots of attempts, but how do they make those attempts different from each other?
They use a couple of techniques during the sampling process when the LLM is deciding its next action or thought. One is using a high temperature.
Temperature. That
Right.
makes the output more random, right? Less predictable.
Exactly. A higher temperature encourages the model to consider less probable options more often, leading to more variation in the sequences of actions. They used a temperature like 1.5, which is quite high. And they combine this with a technique called min sampling.
Min sampling, you mentioned that before. How does that work again, simply?
Okay, so normally an LLM calculates probabilities for all possible next words or actions and picks from the very top ones. Min sampling is a bit more clever. It looks at the single most likely next token and says a dynamic probability floor based on that top probability.
A floor.
Yeah, like a minimum probability threshold. Then it allows the model to sample any token whose probability is above that floor, even if it's much less likely than the absolute top choice.
Ah, so it broadens the pool of acceptable next steps beyond just the very best few.
Precisely. It keeps the output generally coherent, because really low probability options are still excluded, but it allows for significantly more variety and exploration in the generated sequences compared to just picking the top one or two options. High temperature plus MinPAC gives you diverse but still plausible trajectories.
Got it. So high temperature and min-pack sampling generate lots of varied attempts at solving these tasks, some successful, some maybe taking weird paths, some failing, creating a rich data set showing different ways to interact.
Exactly, a spectrum of interactive behaviors and their outcomes.
Okay, so now you have this big, diverse data set of interaction recordings. How do you actually use that to train the model? That's the third component.
Yes, component 3 is the fine-tuning step. You take this collected data set of diverse trajectories, and you use it to teach the LLM to prefer the strategies and sequences of actions that led to better outcomes, like solving the task or solving it faster.
How do you teach it that preference?
They primarily use a method called multi-turn direct preference optimization, or DPO.
TPO.
Right. That's been popular in alignment research lately. It avoids needing a separate reward model.
That's one of its main advantages, yes. Instead of training one model to predict how good a trajectory is, a reward model, and then using that to train the main LLM, DPO directly trains the main LLM to prefer one output over another.
How does that apply to these long interaction trajectories?
They apply it to the entire multi-turn trajectories. They use the outcomes recorded during data generation. Did the agent succeed? How many turns did it take? To implicitly label pairs of trajectories for the same task instance. One trajectory is labeled preferred, for example, the one that succeeded, or the one that succeeded faster, and the other is dispreferred, example, failed or took longer.
So you create pairs of good versus bad or better versus worse attempts.
Exactly. And then you train the LLM using the DPO objective function, which essentially pushes the model to increase the probability of generating the entire preferred trajectory sequence while simultaneously decreasing the probability of generating the dispreferred one.
And why DPO specifically? You mentioned reward models. The paper highlights that DPO is significantly less computationally intensive than many traditional online reinforcement learning methods that might involve training separate reward models or complex policy gradient updates. DPO lets them decouple the data generation phase from the model training phase. You collect all the data first, then you run the DPO fine-tuning. This makes the whole process more scalable, especially with large models and data sets.
That makes a lot of practical sense. Generate data, then train. Cleaner?
It is cleaner, although they do acknowledge that moving to a fully online RL approach where the model's policy is updated while it's interacting and generating data could potentially lead to even stronger results if you had unlimited compute resources. But offline DPO is a very practical starting point.
Gotcha. And they used a variant, RPO.
Yes, mostly they used RPO, which stands for Reward Preference Optimization. It basically combines the DPO preference loss with the standard supervised fine-tuning SFT loss.
Why add the SFT loss back in? Isn't DPO supposed to replace that?
Well, the paper explains that pure DPO sometimes has this quirky side effect. While it learns to prefer the good outputs over the bad ones, it might achieve this partly by just decreasing the probability of all outputs overall, including the good ones. They call this unintentional unalignment.
Huh. So it learns don't do the bad thing, but not necessarily do the good thing more.
Kind of. So by adding back a supervised fine-tuning loss specifically on the preferred trajectories, RPO helps mitigate this. It explicitly encourages the model to increase the probability of generating the successful sequences, not just decrease the probability of the unsuccessful ones. It keeps things better aligned with the goal of producing good strategies.
Okay, that makes sense. So the core training is generate diverse trajectories using tricks like high temp and mint p, pair them up as preferred dispreferred based on outcomes, and then fine-tune the LLM using DP/PO to learn these preferences.
That's the core loop, yes.
But there was a fourth element you mentioned, something about curriculum learning. Optional but useful.
Correct. Component 4 is an optional but potentially valuable refinement. Curriculum learning. The motivation here is all about efficiency.
Efficiency of what? Data generation.
Exactly. Generating those large numbers of diverse trajectories, even synthetically, takes a lot of computation. It's expensive. And crucially, not all tasks are equally difficult for the model at any given stage of its training.
Right. Some might be too easy, some might be way too hard.
Precisely. Spending your limited computation budget generating data from tasks that are trivially easy might not teach the model much new. And spending it on tasks that are prohibitively difficult, where the agent just fails constantly.
Doesn't give you many successful trajectories to learn from in the DPO phase.
Right, you get very little useful learning signal. So the idea of the curriculum is to intelligently prioritize which task groups to sample data from next during that generation phase.
Focusing the effort where it counts the most for learning?
Yeah, focusing on the tasks where the model is currently best positioned to make meaningful progress, where the learning potential seems highest.
How on earth do they estimate learning potential? How do they figure out which tasks are in that sweet spot, not too easy, not too hard?
They get quite clever here. They frame the problem of selecting the next task group to sample data from as another multi-armed bandit problem.
Ah, the bandits strike again. But this time the arms are the task groups.
Exactly. Imagine each of the 10 task groups, 20 questions, mastermind, Wordle, etc., is an arm on a virtual slot machine. Pulling an arm means deciding to generate the next batch of training data from that specific task group. And the reward you get from pulling that arm is an estimate of the learning potential from that task group right now.
How do they measure that reward or potential?
They use an algorithm called UCB, upper confidence bound, which is a standard technique for solving these MAP problems. UCB is designed to balance exploration and exploitation.
So exploring task groups it hasn't tried much lately versus exploiting ones that seem to be yielding good learning results.
Precisely. It looks at how well the model is currently doing on tasks within a group, using metrics like average number of turns to succeed, or the success rate itself, fewer turns or higher success, suggests it's learning. It also considers the uncertainty. If it hasn't sampled much from a group recently, there's high uncertainty about its potential, so UCB might encourage exploring it. Based on this balance, it picks the task group to sample from next.
So the algorithm dynamically shifts the data generation focus towards tasks that seem to be at the right difficulty level for the current model.
That's the intuition. They also mentioned using some predefined metadata to help bootstrap this. Like they use GPT-4 Mini to pre-classify the difficulty of the 20 questions topics into easy, medium, and hard, which helps the UCB algorithm get started.
Clever. And did this dynamic curriculum approach actually help? Did it make training better or faster?
They found that it did. In experiments comparing the curriculum approach against just sampling uniformly from all 10 task groups, the curriculum approach generally outperformed uniform sampling, especially after a few rounds of data generation and training.
Can you give an example?
Yeah, for instance, on the 20 questions task group, after 3 rounds of this cyclical data generation and training, the curriculum approach led to about a 1.4% improvement in average accuracy and a 3.3% improvement in pass at 4 accuracy compared to just using uniform sampling. It helps make sure the most valuable data, the data that provides the best learning signal right now, gets generated and used earlier in the process.
Okay, so we have the full picture now. The PAPRIKA framework involves
1. Designing a really diverse set of interactive tasks requiring different strategic skills.
2. Generating lots of varied interaction trajectories from those tasks using high temperature and min sampling.
3. Fine-tuning the model using DPO or RPO to teach it to prefer the trajectories that lead to better outcomes.
And 4. Optionally using a curriculum learning approach, framed as a bandit problem, to make the data generation process more efficient by focusing on the most promising task groups at each stage.
That's the PAPRIKA framework in a nutshell.
It's a really comprehensive approach. Okay, the big question then. Does it actually work? You've hinted at some results, but let's dig into the experiments. What did they find when they applied PAPRIKA to actual LLMs?
Right, the crucial test. And the experimental results reported in the paper were quite encouraging overall. They applied this PAPRIKA fine-tuning process to two different popular open-source LLMs, Llama 3.1 8B Instruct and Gemma 3 12B IT. Different sizes, different architectures.
And the outcome? Did these models get better at the tasks?
The headline finding is pretty clear. Yes, PAPRIKA fine-tuning significantly improved the success rate of both models across that diverse range of 10 task groups they trained on.
How significant are we talking?
Pretty significant. For the Llama 3.1 8B model, when they averaged its performance across all 10 task types, the PAPRIKA training boosted its success rate by 47% relative to its original success rate before PAPRIKA.
Wow. And nearly 50% relative jump in its ability to solve these interactive problems. That's huge.
It's a substantial improvement, yeah. And they saw improvements for the Gemma model, too, which suggests the method isn't just a fluke for one specific base model. They also looked at past AIC metrics, like does it succeed within AIC attempts, and saw improvements there, too, meaning the model wasn't just succeeding more often, but often finding solutions more quickly or reliably.
Okay, that's impressive on the tasks it was trained on.
Wow.
But you mentioned earlier that it wasn't just about getting the answer eventually. Did PAPRIKA also make them more efficient agents? Better strategists?
Yes, that's another key finding. The results showed that the PAPRIKA-trained models also solved the tasks in fewer turns on average. This was seen across multiple task groups like 20 questions, mastermind, customer service, and others.
Fewer turns. What does that imply?
It's a strong indicator that the model isn't just, flailing around randomly until it stumbles on the answer. It suggests it's becoming genuinely more strategic and efficient in how it explores the problem space, gathers information, and sequences its actions. It's learning to get to the solution more directly, which implies better underlying strategy.
That efficiency point feels really important. It suggests real strategic improvement, not just brute forcing. Okay, but the ultimate test for general capability, the thing we talked about at the start, is generalization, right?
Absolutely.
Can a model trained on these 10 types of tasks apply those learning skills to a completely new type of task it has never, ever seen before during training? Did PAPRIKA achieve that?
This is arguably the most exciting finding in the paper, the evidence they present for zero-shot generalization. And they tested this quite rigorously using what they call leave one out, or LUO experiment.
Leave one out. How does that work?
Okay, imagine they have their 10 task groups. For a LUO experiment, they trained the PAPRIKA model on trajectories generated from 9 of those task groups, but completely hold out or leave out all data from the 10th task group.
So if they leave out, say, murder mystery, the model sees 0 training examples, 0 interaction data specifically from murder mystery tasks.
Exactly. 0 exposure during training to that specific type of interactive environment and its rules or dynamics. Then, after training on the other 9 groups, they test the model's performance on instances taken from that held-out 10th group, murder mystery in this example.
Okay, and the result? Could it play the game it had never seen?
The remarkable result was that these LOO models, the ones trained on the diverse set of other tasks, often performed just as well as, or sometimes even better than, models that were trained only on data specifically from that single held-out task group.
Wait, really? Seeing other games made it better at the unseen game than practicing only that game?
In many cases, yes. It strongly suggests that the skills learned from the broad, diverse set of training tasks, the deduction, the strategic questioning, the exploration balancing, were general enough to transfer effectively and help it tackle the completely novel task type.
That's genuinely impressive. That really sounds like it didn't just memorize how to play the training games, but learn something more abstract, more fundamental about interactive problem solving.
It's powerful evidence for their core hypothesis: learning general strategic capabilities through diverse exposure. They quantified this, comparing the performance of the LOO model, trained on 9 groups, on the held-out 10th group, against the performance of the original base model on that 10th group. They saw improvement on 9 out of the 10 task groups. Seeing the other tasks helped it perform better on the unseen one.
Wow.
They also did another comparison, training a model on the PAPRIKA full set, all 10 task groups, versus training separate models on data from just a single task group, e.g. only Wordle data or only Bandit data.
Yeah, I'm sure.
This showed that even for tasks the model was explicitly trained on, like Wordle in the full set, seeing the diversity of the other 9 task groups often led to better performance on Wordle compared to the model that only saw Wordle data.
So variety helps even for the things you are practicing.
It seems so. It further underscores the benefit of that broad, diverse exposure during training. It seems to build more robust underlying skills.
Did they check this generalization on, like, completely external third-party datasets just to be sure it wasn't an artifact of their own test setup?
Yes, they did. They evaluated the PAPRIKA models on separate data sets from a benchmark called LMRL-GYM, specifically for the 20 questions and Guess My City tasks, which exist in that benchmark.
And did the improvements hold up?
They did. The performance gains and the strategic improvements, like solving in fewer turns, that they saw on their own internal test sets successfully translated over to these external data sets. It reinforces the idea that the generalization is real.
Okay, that's convincing. And you mentioned a specific Wordle test earlier, the one with different word lengths. That sounds like a really strong test of generalization modifying the core rules.
It is. It's a really compelling example, I think, of transferring learned skills to a task variant the model was never explicitly trained on. So remember, the PAPRIKA training only included Wordle games with 5-letter words alongside the other 9 diverse task types.
Right.
For this test, they challenged the PAPRIKA trained model with Wordle games, where the secret word had a different length. They tested it on 4-letter words and also on words ranging from 6 letters all the way up to 10 letters.
So the fundamental structure of the puzzle, the grid size, the number of possible letters per position, was changed in a way it had never encountered during its PAPRIKA training.
Exactly. It had to somehow adapt its 5-letter Wordle deduction strategy, the logic it learned about using green, yellow, gray feedback, to these completely new word lengths.
And could it?
Yes. The PAPRIKA-tuned model significantly outperformed the original baseline LLM on this modified Wordle task across those different lengths. It demonstrated that the underlying deductive reasoning skills and the ability to adapt strategy based on feedback skills honed across the diverse PAPRIKA tasks actually generalized beyond the specific 5-letter rules it was trained on to a structurally different version of the game.
That feels really significant. It's like a concrete example of the AI truly learning how to learn or figuring out a new problem on the fly by drawing on this repertoire of general strategic skills it developed from playing other different games.
It certainly points in that direction.
Now, one concern with fine-tuning models is that sometimes you improve one capability but hurt another. Did PAPRIKA negatively impact the model's basic language abilities? Like, could they still chat or answer questions well?
That's a crucial question. And thankfully, the paper reports that the PAPRIKA fine-tuning did not seem to negatively impact the model's performance on standard language model benchmarks.
Oh, good. How did they check that?
They evaluated the PAPRIKA-tuned models on common benchmarks designed to measure things like conversational quality, MT-Bench, knowledge and reasoning, MNU Pro, and several others covering core LLM capabilities. The results showed no significant degradation compared to the base models.
Phew. That's a relief. It means these new strategic interaction skills are being added on top of, rather than replacing the model's existing strengths in language understanding, generation, or factual recall. They seem to complement the existing abilities.
Yes, that's a positive interpretation. The learned interaction skills integrate well. Now, it's also important, as the paper itself does, to be balanced and talk about the limitations or caveats they observed in the results.
Right. It's never perfect. Where did PAPRIKA show limitations?
While the generalization was strong overall, it wasn't flawless for every single task group in those leave one out experiments. For instance, the improvement on Mastermind in the LO setting, training on everything except Mastermind, was pretty minimal. And they even saw some cases of slight negative transfer for Wordle in certain LOO scenarios, meaning seeing the other tasks actually made it a tiny bit worse at Wordle than the base model in that specific setup.
Huh. So seeing a diverse set of tasks is generally a big win, but it's not a guaranteed silver bullet for instantly achieving perfect zero-shot performance on every single conceivable new task type.
That seems like a fair assessment based on their results. They hypothesized that maybe scaling up the sheer number and variety of task groups even further could potentially help smooth out some of these remaining generalization gaps.
Makes sense. More variety might cover more edge cases or types of reasoning. Any other limitations?
Another one popped up specifically in the bandit task results. Remember the explore-exploit problem?
Yeah, finding the best slot machine.
While they saw clear performance improvements when the number of arms or choices was small, say 2 to 4 arms, that performance gain kind of vanished when they tested the model on bandit tasks with a much larger number of arms, like 8 or 16.
What does that suggest? Why would it work for few options but not many?
It likely indicates a potential limitation in how well the general strategic exploration principles, learned solely from this offline training on a fixed set of tasks, can scale up to highly complex, large-scale exploration problems. Problems like multi-armed bandits with many options might require extremely extensive exploration or very specific adaptive strategies that are perhaps best learned through task-specific training or, as they mentioned, moving towards online reinforcement learning methods for those really complex scenarios.
Okay. So the offline synthetic data approach is powerful for building general skills that transfer well to many new tasks. But there might be limits to its effectiveness purely zero shot when you get to tasks requiring extremely deep or broad exploration or maybe very niche strategies.
That seems to be what the bandit result suggests. Offline training is a huge step, but it might not completely replace the need for online learning or task-specific tuning for the most complex interactive challenges.
Got it. So to sum up the results, big overall improvements in success rates and efficiency on the training tasks. Really impressive evidence for zero-shot generalization to new tasks, including structurally different ones like variable length Wordle. No harm to core language abilities, but acknowledging some limitations where generalization wasn't perfect or didn't scale infinitely, particularly for very large exploration problems like bandits with many arms.
That's a very balanced summary of the experimental outcomes reported.
Okay, so stepping back from the technical details for a moment, what does all this research, the PAPRIKA framework, these encouraging results, what does it ultimately mean for you listening to this, interested in where AI is going? Why should this work on teaching AIs to be, well, curious and strategic agents matter outside of a research lab?
I think this research represents a really significant step forward. It moves us beyond AI systems that are just sophisticated text processors or experts,
Yeah.
only on the narrow tasks they were explicitly trained for. It pushes us closer to developing truly autonomous agents. Systems that can actually engage with complex, maybe unknown environments, gather the information they need strategically, and figure out how to solve novel sequential decision-making problems without needing us to handhold them or program them for every single specific scenario they might encounter.
That's the key difference, isn't it? Moving from an AI that can do task X because it was trained extensively on task X to an AI that can figure out how to do task Y because it learned the general skills needed for interactive problem solving from its training on tasks A, B, and C.
Exactly. That shift unlocks a whole new level of potential AI capability.
What kind of potential, what could these more generally capable agents do?
Well, it really opens up possibilities for building AI systems that are much more adaptable, more resilient, and more capable of tackling challenges we haven't specifically anticipated or prepared them for with custom datasets.
Like what kind of challenges?
Imagine AI agents that could navigate complex software suites in an office, figuring out which menus to click, what forms to fill across different applications to achieve some high-level goal you give them.
Like book travel for my upcoming conference.
Potentially, yes. Or agents that could gather information strategically from lots of disparate online sources to perform complex research tasks. Or perhaps even more ambitiously, assisting with scientific discovery
How would that work?
by interacting with complex scientific simulations, perhaps. Or maybe even controlling aspects of experimental setups, gathering data, observing results, dynamically adjusting parameters to explore a hypothesis. The paper actually references related work and benchmarks like Science World and Aviary, which are specifically designed to evaluate agents in these kinds of interactive scientific reasoning environments.
So Paprika is building the foundational skills needed for AI to operate in those kinds of demanding, open-ended domains.
That's the idea. This work contributes crucial capabilities needed for AIs to succeed there.
That really brings the concept of an AI agent to life, doesn't it? Not just something passively processing information, but something that can act intelligently and strategically in a world, even a simulated one, to achieve complex goals. So, what's next? Where does this research go from here? What future directions did the paper point to?
The authors outline several really exciting avenues for future research. One obvious one is to explore using those online reinforcement learning methods we talked about.
Where the model learns and updates its strategy in real time while it's interacting.
Exactly. It's more computationally expensive, but it might allow the model to learn even deeper, more complex strategies, especially for those really hard exploration problems.
Makes sense. What else?
Another fascinating, almost sci-fi direction they mention is the idea of teaching LLMs to automatically generate new, suitable tasks or interactive environments for training other AIs.
Whoa. instead of humans designing all these diverse training games.
The AI itself could potentially invent novel challenges, perfectly suited to push the boundaries of another AI's capabilities. It could help overcome the massive bottleneck of human effort required in designing these rich training environments.
AI creating the curriculum that other AIs use to become smarter and more general. That feels like a potential game changer for scaling this kind of training.
It would be a significant breakthrough if it works reliably, yeah. They also mentioned refining the curriculum learning algorithm itself, the UCB part, maybe making it less dependent on having those predefined task groupings or needing external tools like GPT-4 Mini to estimate task difficulty upfront.
Making the curriculum generation more autonomous too.
Right. And of course, as we touched on with the generalization limitations, simply scaling up the number and the types of diverse task groups used for the initial PAPRIKA training could further enhance the breadth and robustness of the generalized skills the model learns. More variety is likely better.
And just to quickly recap the limitations they acknowledge about the PAPRIKA approach itself as it stands now.
Right? It's important to remember those. They acknowledge that PAPRIKA currently seems to work best when you start with a reasonably capable base LLM, one that can already generate somewhat coherent initial trajectories for the DPO training to latch onto.
You need a decent starting point.
Seems so. And as mentioned, the current work mostly used offline methods, di properto, due to compute constraints, whereas online RL might be more powerful eventually. And finally, while the curriculum learning helps automate task selection, the initial design of those diverse task environments and specifying their rules still required significant human effort. That's why the idea of AI-generated tasks is so compelling for the future.
Okay, so pulling it all together for a final summary. PAPRIKA offers this novel, scalable approach to train large language models to become much more capable, interactive agents.
Right, by fine-tuning them on synthetic interaction data collected from a wide array of diverse strategic tasks.
The framework successfully gives them general strategic decision-making and exploration skills. And the core achievement, the really exciting part, is that demonstration of impressive zero-shot generalization.
Showing that these learned abilities actually transfer effectively to new, unseen interactive tasks, making the models more efficient and successful problem solvers even in novel environments without needing specific training for those environments.
It feels like it shifts the focus, doesn't it? From training models just to perform specific known actions and known scenarios, to training them to possess the general ability to figure out how to act strategically and learn from feedback in almost any interactive scenario, even one they encounter for the very first time.
That's a great way to put it. It's about teaching the process, not just the solutions.
It paints this picture of an AI that learns to be genuinely curious, capable of intelligently navigating and solving problems in new situations, simply because it has, in effect, played a vast variety of different synthetic games and learned from the outcomes, good and bad.
It's definitely a very promising direction for building more adaptable, more capable AI systems that can truly function as autonomous agents in complex worlds, whether digital or eventually physical.
Which brings us to this final thought for you, our listener, to mull over as you reflect on this deep dive. If we are indeed getting better at developing AI systems that can learn to be generally curious, strategic learners, essentially learning how to learn through interaction in diverse simulated environments, how might that fundamentally change the way we envision and interact with intelligent systems in the maybe not-so-distant future?
Yeah.
Could this capacity for learning the process of intelligent exploration unlock entirely new possibilities we haven't even thought of yet? Maybe in scientific discovery, complex systems management, or even just how we interact with our digital tools day to day? Or, conversely, does it raise new, perhaps surprising questions about the nature of AI agency, about creativity and problem solving, and maybe even about how we define intelligence itself when it's learned primarily through simulated rather than real-world experience?